fluid mechanics, and now I do fluid mechanics where I do fluid mechanics, and then I'm going to do fluid mechanics.
Welcome to video number 5 in fluid mechanics. Okay, so in video 5 here, we're continuing along in section 2, which is about fluid statics. And we can see from this outline, so we're now on section 2.3, which is called hydrostatic force on submerged surfaces. So what we're going to focus on in this video is how do we figure out the force on an object that's located within a fluid. So these objects, for example, will be at a certain depth, and so they'll have a pressure acting on them, right? That's a function of the depth. So you can think of like a submarine, for example, or like a gate that's located like within a big tank that's holding fluid. Okay, you'll see the examples of these as we go along. And we're going to figure out the force that's acting on these due to the fluid. And since it's static, of course, those are the normal forces, which are the pressure forces. Now, as I've mentioned, right, I would normally do examples, so it's very helpful to see the examples side by side with the explanation here, but I'll do those in separate videos. So that's example 2.2, 2.3, and 2.4. I'll do separate video for those for convenience sake, but those really do go alongside with this video here. Okay, now we can get started here looking at the hydrostatic force on submerged surfaces. Okay, so now that we've established how we can calculate the variation of pressure within these systems of static fluids, the next question then becomes, how do we calculate the forces resulting from these pressures on submerged surfaces? And as I mentioned in the intro to this chapter, as mechanical engineers, this is oftentimes what we have to calculate. So for example, the force that would be acting on a gate or a panel that's located on a large reservoir or a large tank of fluid. And in some of this analysis, we're going to be borrowing from what you looked at in your statics course, but because we're dealing with fluids here, the analysis is going to be different in many ways. So that's why some of this might look familiar, but there's a new twist on it because we have the forces that are resulting from the liquids. So firstly, when we're asked to calculate a force on a submerged surface, we need to remember 3 things. So we have to specify the magnitude of the force, the direction the force is acting, but also the line of action of the force, meaning like where on the surface is the force actually acting. So to understand what we're trying to calculate here, let's look at this picture. So it's showing a tank where the liquid surface is denoted with that triangle here, and this tank has an angled side on it with the surface shown in gray there. And now we're asked to calculate what's the force exerted on this surface as a result of being submerged in this tank. Okay, the first thing we note here is how we write our coordinate system. So because we're going to be calculating the forces on this plate, it makes sense to align our coordinate system with the plate. So you see that Y was drawn there so that it follows along the plate surface. Now the Z coordinate is shown as normal to that surface. And then we look at our overhead view to see the Y and X coordinates against the surface of this plate. And we remember in fluid statics, there are no shear stresses. Everything must be a normal force. So we know we can show the resultant force as being normal to this surface because there only can be normal forces acting on it. And then as we've done previously, we want to calculate what these terms are for a differential element, and then eventually we'll sum all those to get what the total force is acting on the plate. So the differential element is shown here in the overhead view with area of dx times dy, which equals dA. Okay, so we need to figure out the pressure force then that's acting on this element. So we look at that first. Okay, now in lecture, I normally stop here and ask you, how do we relate pressures and forces? So I'm going to write the force here, and we need to know what the force is on this surface. So I'll let you think about that for a second. So we know that the pressure itself is the force divided by the area it's acting over. So if we want to calculate the force, we need to take then the pressure and multiply it by the area that it's acting over. Okay, we want the resultant force acting over the whole area. So then we just have to add up all these little dAs over the entire surface there, and that gives us the resultant force. And this summation is accomplished by integrating. So when we integrate this, we have the resultant force is the integral over the area of P times dA. Okay, and I boxed that because we can actually solve the problems using this integral form. We're going to see that there are 2 ways to solve this problem. I'll denote them as method 1 and method 2 so we don't get confused. Now I prefer to use the integral method, but there are pros and cons to both, and I'll discuss those as we go through this. So I'll label this as method 1 and the integral method. Okay, now let's pause, take a look at this, and figure out how we would solve this integral. So remembering back to calculus, we know when we take an integral of pressure times dA, we're going to need to know how the pressure changes over the area. That's what this integral is saying. But for an incompressible fluid, we just figured that out. We figured out for these static fluid cases how the pressure varies. Okay, so this is what method 2 is really doing here. What we're doing is simplifying this integral a little bit further because we know the pressure distribution for an incompressible fluid. So now if we assume we're looking at incompressible fluids, we can simplify this down from an integral form into an algebraic form. And we're going to go ahead and do that here. So let's write that out here, and then we'll relate how this pressure varies over this area that we're trying to solve for. Okay, so the pressure equals P naught plus rho GH, where the P naught term is often the surface pressure or some reference pressure that we know. So we look back to the figure for the case that we're solving, where we know the pressure at the surface is going to be the ambient pressure as listed here. But from what we calculated previously, that's going to be a function of the depth of the fluid, so this H coordinate shown here. So we're going to have to relate that depth to our surface, and we do that using some simple geometric relationships. So I'll show that below. Okay, normally I wait in the lecture for someone to figure this out, so I'll give a pause here so you can tell me how we relate H back to the X and Y coordinates. Okay, it's y sine theta. Okay, so we go ahead and sub both of those things in here. Okay, so we go ahead and do this integration. So I'll split the terms and collect the constant terms. Okay, we pause here for a moment and examine this expression. So if we were going to use method 1, the integral method, we can see how we can normally plug in for the pressure. And then what we would do is this integration that's on the right-hand side here, we would break out that dA term into dx dy and proceed with just solving the equation from here. Now I'm going to show a number of examples, so we'll see this done with both methods a few times. But what's going to let us proceed to method 2 here is we recognize that in this expression, we have a term that comes up a lot, and we should have seen this quite a few times in fluid statics. So if we just look at this integral term here, the integral of y dA, I'll give you a second to see if you can remember what that is. Okay, now hopefully some of you recognize this as the first moment of the surface area about the x-axis, which can be written like this, where y sub c is the y coordinate of the centroid. Okay, so let's sub that in, and we can rewrite sine theta times yc just as the height at the centroid. And then finally, we can recognize this term in brackets, P naught plus rho GHC, as just the pressure at the centroid location. Okay, so then if we substitute for that term, P sub c, which is the absolute pressure at the centroid, we have the following. Okay, so in this expression, it seems like a fairly simple way to calculate the magnitude of the resultant force because it's just the pressure at the centroid location times the area. We remember that's the absolute pressure of the centroid. And it'll become clear in a minute why I keep saying absolute pressure. Okay, so as I mentioned, we refer to this as the centroid, and it comes up, and it has a name and is often tabulated because it comes up so much in static calculations. So I've shown a few sections of a table here where we can see the kind of things that come up. So oftentimes the centroid on these surfaces will be shown, as well as things like the second moment of area, which we'll see as we continue our analysis here will become important. So this type of thing will often be given to you on an exam, and I'll continue to refer back to it as it's needed throughout this discussion here. Okay, so I kept saying that resultant force was the absolute pressure at the centroid. Now, why was I making that distinction? So let's look back at our figure for the case that we're analyzing here. Oftentimes, when you have a gate or a surface located on the side of a tank, on the opposite side of that, you have ambient pressure. Generally, it's just exposed to the atmosphere, so usually air. So in this figure, what we've done is draw out all the pressures acting on this surface. So we have the ambient pressure that's acting on both sides. It's shown by that constant distribution there. And then in the liquid side, we have the additional component at each location that's due to rho GH. So if the ambient pressure is acting on both sides, the effect will cancel itself out. My 8-month-old daughter is in the background again, so those noises are her. And I swear, if you could see her face right now, you'd think she was totally making those noises on purpose. She's literally totally quiet until I start talking. And I swear she's smirking at me right now. Okay, so as I was saying, they'll cancel out. So if that term cancels out, then in essence, what we can do is just subtract the P naught component from the liquid pressure distribution, And then what we've done there, once we've subtracted out the P naught term, is we're just left with gauge pressure, because gauge pressure is just absolute pressure with atmosphere subtracted from it. So in a huge majority of these cases, we'll have the atmospheric pressure acting on the backside of the surface as well. So what we can do is just use gauge pressure instead of absolute pressure. Okay, so that gets us part of the way. Now we know how to calculate the magnitude of the resulting force, and we know its direction because it's normal to the surface, but we still don't know the location of where it's acting. And if we remember back to statics, it's very important to know the location the resultant force is acting at to be able to properly account for that in the design and material we use for these plates here, calculating the moment and things like that. So we denote the location that the resultant force is acting as x prime and y prime, and then the strategy we use to calculate this is we say that the location of this force, when we look at its moment, so its location y prime times the force, that's the moment, that also has to equal the moment that results from the y coordinate times the distribution of the pressure on the right hand side there. Okay, so in the form we've written here, this is the integral form. We're calling this the first method, and we could go ahead and solve it in this form. And again, I'm going to show a number of examples of this, so don't worry, we're definitely going to get to see it. And as I mentioned, I'll do that in the follow-up video to this one. But we can also simplify it to what we're calling the second method, so we can put it in an algebraic expression. And to do that, we make a few assumptions. And again, I will show this in the examples, but generally when we go here from the first method to the second method, that would be for simple shapes where these assumptions apply. So we make these assumptions, we simplify from integral form to algebraic form. Then to solve that expression, we're going to need to know things like the centroid, second moment of area, etc. Okay, so for now, let's just get this from the first method into the second method, and then we'll see all of this done, which personally I think is a better way to see it. We'll see it in the examples that follow this. So then it's the same strategy we used before. We'll have to integrate this term on the right, and we do that by writing the pressure as a function of the y coordinate. Okay, so we do the same substitutions as we did before, but in this case it's multiplied by the y coordinate, so we just have to remember to multiply the y coordinate throughout. Then we do the substitutions. Okay, so let's collect up these terms and simplify. Okay, now again we have some terms that come up a lot, so we should recognize this one already. And we'll have come across this one as well, so I'll see if you can remember what this one is for a second here. And hopefully some of you remembered that that's the second moment of area about the x-axis. We denote that as IXX normally. And then typically what you'll find in tables is the second moment of area about the centroid. And we can use the parallel axis theorem to just transfer to that. So then we'll have the value that's commonly found in the tables, which will simplify our calculations, of course. So then we sub in. And so now anytime we see the I with the subscript XX and they have the little hats over them, that's referring to the second moment of area about the centroid, which is what's commonly tabulated. Okay, so we'll collect up all these terms and simplify so the equation is more manageable. And I've shown the terms there grouped in purple that can be simplified. So we recognize first the height at the centroid position, and then we recognize the resultant force term there. Now what we're calculating for is y prime location, not y prime times the resultant force. So we simplify for this by dividing through by FR. And so then we have the final expression for how we calculate the location given here. Now as before, we will very commonly have the same ambient pressure acting on the backside of the surface that we're calculating for. So if we go ahead and sub that in, we can further simplify this expression just one more step. So the resultant force in that case would be the gauge pressure at the centroid location times the area, which we can simplify to. And so then we can sub that in and we get the following expression here. Now for those cases where it's not the same pressure acting on the other side of the plate, we'll just make a quick note here on how you'd address that. So the strategy for that then is you could either just calculate what the force ends up being on both sides of the plate. So you basically just do two calculations, one for each side. Or in some cases, you might be able to simplify the pressure distributions from both sides into just one pressure distribution on the one side by, for example, subtracting the pressure that's acting on the other side. So when you end up with that one distribution, now you could just do the force calculation for one side of the plate. Now we'll also need the X location for where the resulting force acts on the plate. And I'm not going to do the entire analysis again. It's the exact same analysis for the X location. So we'll just write down the resulting equations here. Okay, and I'll label these for which ones are integral and which ones are going to be the algebraic approach. Now this can be a little bit complex. So what I want to do is a number of examples here so we can really use all all these equations in practice, see how they're used, and also I'll do it by the first method and the second method both, so we can get a feel for exactly what the pros and cons are for each of these methods. Okay, now for curved surfaces, the analysis is going to be very similar to what we did above, but we're going to employ kind of like a trick here that'll help us solve these questions. So what I'll first do here is we'll look at how we calculate forces, right? So we know from our analysis before, that's the pressure times the area. We're working on this small differential scale. So our area is dA, but when we say dA, actually dA is a vector with a normal that points outward from the surface. And so it actually has components, x, y, and z components, as you can see there from the figure. So when you calculate the resulting force, you integrate this pressure over this area, and then that resultant force, right, has an x, y, z component. So if we look, let's just look specifically at the x direction. So we'll take the resultant force in the x direction. And so the way we get that, right, from our resultant force is we take the dot product with I, which is the x direction, right? We're left with the expression at the right there, which says it's the integral of the pressure times dAx. Now, the reason we're doing this is because we just want to remind ourselves that vectors have these three components and they can be broken out. So when we talk about what dAx is, like what does that actually mean, we can see from the figure here that that's actually just the projection, right, of that area dA projected onto the plane that's perpendicular to the x-axis, right? And then similar for y and z, you project it onto those three planes. And so all this is to say really that anytime you have a vector like the resultant force, you break it out into components that are actually projections. So we're going to use this idea that we can just break out the force into these projected areas to help us calculate curved surfaces. And I've just have an expression there that writes it more generally, right? So that's subscript L just kind of denotes any direction, and we write it generally there in this expression. So now let's flip over to see how this idea of these projected surfaces can be used to help us solve for curved submerged surfaces. So we have a tank full of fluid and this curved surface located in it. That's shown on the left there, where we denote the surface of the liquid with the triangle, and the curved surface located within the tank is here. And so what we can then do, as the figure shows, is break this out into all the horizontal forces and all the vertical forces, and then we'll add the two to get the total. When we look at the horizontal, we can imagine ourselves beside this curved surface, looking at it from the left-hand side here. And so the horizontal projection would be this gray surface shown here. And that's the projection of this surface in that horizontal direction. And we again have the pressure variation with depth in this case. And we can see, I think, fairly quickly that that projected surface there is just exactly what we calculated previously. So we'll have forces in the x and y direction, and the calculation is exactly identical to what we did above. Okay, we also have to account for the vertical force, which is different to what we just did. So let's take a quick look at what that works out to be. Okay, now in the vertical case, we can't just project this on the bottom, but let's think about why that is. So I'll give you a moment to think about why we can't project onto this bottom surface here in this case. So that's because if we project it to the bottom surface, we have a pressure that's a function of depth. So we can't project to the bottom surface because the pressure at the bottom there is different than the pressure that's pushing against this curved surface in the vertical direction. So for example, if we project it onto that plate there, we'd have one pressure here. It would be completely different than the pressure that's actually pushing down on this surface, which is located there. So we're going to use a slightly different strategy. We're going to plug in for the pressure here and then see what happens to our equation. Now we have this H times dAz term here, and if we look at our figure for a second, we can see what that translates to. So when we integrate H times dAz there, all those little slices, we end up with the volume, the liquid volume above the curved surface that I'll shade in here. So we can rewrite this then, and integrating the differential volume element over the volume, density and gravity won't change over the volume, so we simplify to rho GV. Now we can summarize. The horizontal force we calculated just like before. The vertical force now is rho GV, and we notice that rho GV is actually equal to the weight of the liquid that's located above this surface. So the only thing remaining is that we need the location of where FV, the vertical force, is acting. So we note that the line of action of the vertical force, it acts through the center of gravity of that volume. Okay, so that's the end of video 5 here. but I really can't stress this enough. So as part of this video, in the past, I would have done 3 examples included in this video here, but I was asked by past students, for the sake of convenience, I'm going to put these in 3 separate videos, but I really want you to remember that the 3 example videos that follow this video, they go hand in hand. So on the one hand, you can't understand how to do those examples without seeing video 5, right? The basic explanation of how you calculate submerged surfaces. But also just watching video 5 here, just having an explanation of how to calculate these submerged surfaces, I don't think also that's not enough to really be able to completely understand what's going on here with forces on submerged surfaces. Okay, so just a quick summary here. In this video, we looked at how you calculate forces on submerged surfaces. And again, we broke it down from sort of the more simple to the more complex. So we looked at, a flat surface, like an inclined surface. We expanded and looked at curved surfaces. And when I do these examples, I'm going to do the same thing. I'll start with sort of a simple flat inclined surface. Then I'm going to look at different shapes, so how you do the calculation when it's not just a simple rectangle. And then a curved surface too. So we can see all of the material I just covered. We're going to see examples for that. Okay, then the lecture that follows those, we're actually going to finish up section 2. We're going to look at buoyancy and stability. So we'll talk about how you figure out if something floats. We'll look at boats, stability of boats and submarines, hot air balloons, that kind of thing. Okay, that's all for video number 5.
Bye-bye. Bye-bye.